Hi there, my name is Dr. Dorothy Buckley, and it is my pleasure to welcome you to this video where I will be talking about working memory. So in my previous video, we talked about um, short-term memory, which is the term that most people are familiar with. So, short term memory was one of the processes that Atkinson and Shiffrin sort of conceptualized in their modal model. And Broadbent also talked a lot about his short term memory in his model as well. And so, short term memory, also known as immediate memory or primary memory, is essentially a type of memory that details the current contents of your consciousness, right? So, whatever you're currently thinking about is kind of what occupies your short term memory store. But short term memory has its limitations, if you will. So it's a limited capacity system with a very, very brief duration, not quite as brief as sensory memory, but on the order of about between 18 and 30 seconds, right? And so when Broadbent and Atkinson and Shiffrin were thinking about short term memory, they basically conceptualized it as a limited capacity system for the temporary storage of information. And really, according to those memory theorists, all you should be able to do with your short term memory is use rehearsal strategies to keep whatever is in your consciousness available, right? So if I were to give you the numbers 5237, all you should be able to do in terms of your short term memory process is hold on to those numbers through the process of rehearsal, right? So pretty much all you can do with your short-term memory is say 57 or 5237 over and over and over and over, right? But people quickly became disillusioned with the notion that short term memory was just a temporary storage system for whatever occupies your consciousness. So, why did they become disillusioned with this idea? Well, uh, psychological scientists like Alan Badley, for example, quickly realized that despite the fact that short term memory was theorized to be a limited capacity system, people could often do things that were believed to um, fill up your short term memory, right? So, according to the original model of short term memory, if you were to think of 4 to 7 numbers, say, right? So going back to the 5237 example, simply rehearsing those numbers should maximize your capacity of your short-term memory. So if you're focusing on rehearsing those 4 numbers, you shouldn't be able to do anything else. But what Alan Badley and colleagues quickly discovered is that people were able to do multiple things at once. So they were able to multitask, right? So, for example, if I were to ask you to maybe read a sentence, right? Not only read a sentence, but understand it in terms of your comprehension, right? So if I were to give you a sentence like, Mary Alice wanted to be a nurse just like her mother, right? So if I asked you to read that sentence and also keep in mind those 4 numbers, 5237, people could do that quite easily, right? And that was a problem because, again, Short-term memory was theorized to be a limited capacity system that could only hold on to a limited number of information. So the fact that people were able to multitask and do more than one thing at once, when both of those tasks were believed to necessitate short term memory, was a problem, right? Another limitation of the model of short term memory as a temporary storage system is that people were often able to not only store information, but to manipulate it, right? So not only can I hold those numbers in mind, 5237, I can also subtract 37 from 52. I can multiply 52 times 37, right? I can divide those two numbers. I can talk about whether they're prime numbers or not, right? And that's not because I'm some kind of, mathematical genius. All human beings are able to do that. So, what scientists did eventually is they changed that conceptualization of short term memory to what's called working memory. Right? So, working memory is an updated model of short term memory that includes both a storage component as well as a manipulation component, right? So not only can we hold on to information, we can also manipulate it or process it in additional ways, right? So, so when we talked about short-term memory, we talked about people like uh, like Tomohiro Asada, right? Who was able to perform mental calculations competitively, right? And also to apply kind of pre-learned tricks for making mathematical calculations involving large numbers, right? And that's kind of a classic example of working memory. So we use working memory for mental arithmetic and calculation. We use working memory for reading comprehension. We use working memory for putting words into alphabetical order, and for considering multiple sentences, like, right, when we're reading and trying to comprehend things, right? So these are all examples of how we might utilize working memory effectively. So another interesting finding that Alan Badley and colleagues discovered that made them kind of switch to this model of working memory as opposed to short-term memory was that when they gave people two tasks to complete at the same time, again, they were able to do it effectively. So in this case, they gave people a digit span task, which is very similar to what we talked about before. So they would have to hold in mind, an increasing list of numbers, while also performing what was known as a grammatical reasoning task, right? So for the grammatical reasoning task, they would see text like A follows B, and then they would see a little diagram like the one you see in the second column there. So B and then an arrow A, right? And so they would basically have to say whether that diagram was true or false, right? So if the rule is that A follows B, a diagram depicting B following A would be false, right? And Bagley discovered that people were able to do this very, very easily. So they could hold in mind an increasing number of digits while also performing this grammatical reasoning task, right? So again, what that suggested is that the original conceptualization of short-term memory that thinks about this intermediate state of memory as being just a temporary storage system was inaccurate, right? So people are able to multitask and perform multiple tasks at once while also taxing their short-term memory beyond the limited capacity as it was originally conceptualized, right? So again, working memory is an updated model for short-term memory that includes both multitasking and also one's capacity for both storing and manipulating information. So, the most well known model of working memory that most people are familiar with is Badley and Hitch's 1974 multi component model of working memory. And it's so called the multi component model because, unlike short term memory, which is just a single construct, the multi component model sort of reasons or conceptualizes working memory as consisting of multiple components. Right? So, this depicts actually the most up to date multi component model of working memory that Badley and Hitch last updated, or I should say, Badley and colleagues last updated in 2012. Um, but basically, the multi component model consists of what Badley and colleagues conceptualized as slave systems. Okay? And the slave systems consist of primarily the visual spatial sketchpad and the phonological loop. Okay? So basically, the visual spatial sketchpad is responsible for coordinating visual and spatial information in working memory, and the phonological loop, very similar to the Atkinson and Shiffrin model of short-term memory, is responsible for processing basically auditory and verbal information. But one thing to keep in mind is often when we see a list of numbers, right? So if I show you, for example, a clock on the wall and you have to see what time it is, right? Oftentimes that information will be processed in um, the visual spatial sketchpad, but the numbers will be converted into a speech like code. Okay, so because the numbers are also converted to a speech like code, we would say that a clock, for example, is kind of dually processed in the visual spatial sketchpad and the phonological loop. And certainly, if I gave you a list of numbers, right, like in my previous example, 5237, even if you saw a picture of those numbers or if you saw those numbers on a computer screen, okay, what would happen is you would convert those visual symbols of the numbers into a speech like code, and that would allow for rehearsal. Okay? So the first thing we're going to talk about is the phonological loop. Then we're going to talk about the visual spatial sketchpad. And then we're going to move on to the other components, including the central executive and the episodic buffer. So the phonological loop, as I mentioned earlier, is really very similar to Atkinson and Shiffrin and Broadbent's conceptualization of short-term memory. So basically, the phonological loop consists of two components. First, there is the phonological store, which is basically just a repository, if you will, or storage system for all incoming auditory and verbal information. And then there's a component known as the articulatory rehearsal mechanism, or the ARM. And so basically, the articulatory rehearsal mechanism, just like it sounds, is a kind of like an internal record player, if you will, that allows you to convert the incoming information into a speech like or verbal code and then rehearse it, right? So, if, for example, you see a list of words, boat, house, cat, animal, ice cream, okay, all of those words are going to are going to come in and get temporarily stored in your phonological store. And then the articulatory rehearsal mechanism is going to help you convert them into speech so that you can say those words over and over and over again to yourself, and therefore kind of maintain them continuously through that rehearsal into your phonological loop. So, what we're going to talk about now are experiments that support Badley and Hitch's conceptualization of the phonological loop. So, one of the earliest experimental demonstrations that seems to support this idea of the phonological loop um, were experiments looking at phonological similarity. So basically, phonological similarity just refers to the fact that when we present people with similarly sounding words or letters or numbers, they're more likely to make errors in terms of their later recall of that information. And the reason why people make errors when words or letters sound the same is because in order to encode that information into your working memory, you're essentially saying it aloud to yourself. So if it sounds similar and you're speaking it to yourself, it's inherently going to be more confusing if the items rhyme or sound similar. Okay, so in this graph, this shows the effect of phonological similarity. So when you ask people to memorize BCTVP, for example, they're not going to recall as many of those letters as they would for a list of non-rhyming letters, such as EQLWF, right? And so this was demonstrated repeatedly through multiple experiments by Conrad and Badley and others. And they saw similar findings, by the way, with rhyming words, right? So people would have more difficulty remembering cat, bat, hat than they would hat, shirt, pants, for example, right? So it's more difficult to remember words that rhyme, for example, than words that have similar meanings, at least when you're using your working memory. Right? So, what other evidence do we have in addition to phonological similarity that supports this conceptualization of the phonological loop? Well, there's also a really interesting finding called the word length effect. And it basically is the fact that the number of words that a person can recall in their short term memory is directly related to how long it takes to pronounce those words, right? And this happens because words are maintained in the phonological loop, right? So they're processed and maintained through articulatory rehearsal, right? So you're quite literally speaking the word to yourself, right? So if the word takes longer to pronounce, you're going to have less time to rehearse the word, which means it's not going to be encoded as well into your working memory, right? So this was first demonstrated by Badley and Thompson and Buchanan and colleagues in the 1970s, right? So basically, for example, if you gave participants a list of words such as, let's see, so if you gave participants a list of words like, so for example, when long to pronounce words like baboon, weekday, or foresee are compared to short to pronounce words like picket, rugged, and pistol, participants recall more from the short to pronounce group than the long to pronounce group, right? And again, it's basically in reference to the fact that shorter words take longer to pronounce or take less time, to pronounce. So you can basically say them aloud to yourself more times than you can for longer to pronounce words. So, as I mentioned earlier, really the essence of the word length effect is not the number of syllables or how many letters the words are comprised of, but rather their pronunciation time, right? So, the longer it takes you to pronounce a word, um, the the harder or the more difficult it's going to be for you to recall those words relative to shorter to pronounce words, because shorter to pronounce words profit from more rehearsals in the phonological loop, right? So a lot of experiments have demonstrated the relevance of pronunciation time to the phonological loop in particular. So, for example, Ellis and Henley in 1980 looked at digit spans, or how many numbers you can maintain in your phonological loop, specifically for children in Great Britain. So they focused their testing on the part of Great Britain called Wales. So in Wales, there are still people whose first language is Welsh, which is a derivative of a Celtic language, basically, rather than English. So when you speak Welsh, the word for digits take longer to pronounce than they do in English. And this is largely because Welsh vowels take longer to pronounce than their English counterparts. Therefore, it takes more time to count from 1 to 10 in Welsh than it does in English. So Ellis and Henley examined digit spans in Welsh English bilingual children, and consistently, the children's digit span was longer in English than it was in Welsh. Because the words mean the same thing in both languages, and because most of the targeted students were more fluent in Welsh, the digit spans must be different because, at least for the names of digits, one can say the digits faster in English than in Welsh. So in the word length effect, the independent variable is the length of the words, and the dependent measure is whether or not the words are recalled, right? So a short time later, in a second study, they confirmed the same finding using different languages. So Nevaeh, Benjamin, and Aries in 1986 also made use of the fact that digits take a different amount of time to say in different languages. So, for example, in English, the number one is pronounced one, which is one syllable. In Spanish, however, the number one is pronounced uno, which is two syllables and takes a little more time to say than it does in English. Therefore, uno should occupy slightly more of the capacity of the phonological loop than does the English version, right? So they tested students at the University of Israel, where they were able to examine fluent speakers of four languages: English, Spanish, Hebrew, and Arabic. And in terms of pronunciation time, it takes the least amount of time to count from 1 to 10 in English and the most amount of time to count from 1 to 10 in Arabic. So when the digit span task was presented to speakers of each language, the digit spans reflected the pronunciation times. So the digit spans were longest in English, followed by, in order, Spanish, Hebrew, and Arabic. This decrease in digit spans is related to the increase in pronunciation time of the digits in each language, right? Therefore, these results support the idea that pronunciation time is relevant in evaluating the capacity of working memory and specifically the phonological loop. So another piece of evidence that supports the phonological loop, and specifically the importance of rehearsal for the phonological loop, or for information stored in the phonological loop, is something called the articulatory suppression effect. So basically, if you have people trying to learn a list of words, right? So let's say people are trying to learn a list of both short words and long words, and for some of the lists, you have them repeat the word the the over and over again while they're studying the words, or a sound like fa, fa, fa aloud while they're studying the words. Basically, because they are speaking aloud, that prevents the articulatory rehearsal mechanism from engaging and converting those seen words into speech, right? So basically saying the out loud, or any other word out loud, while you're trying to encode speech-based information into the phonological loop, vastly disrupts that process. So people's recall for those lists of words goes down significantly. And in fact, if we have people learn these words under the articulatory suppression condition, where they're saying the or fa or whatever random sounds out loud, we see no word length effect, right? And that's because if they can't engage in rehearsal at all, right, pronunciation time or word length isn't going to matter, because none of those words are being converted into a speech like code by the articulatory rehearsal mechanism. Other evidence that supports the existence of the phonological loop comes from research on what's known as the irrelevant speech effect. So the irrelevant speech effect refers to the observation that the performance of the phonological loop is mildly impaired when talking occurs in the background. Right? So irrelevant speech affects performance on phonological loop tasks, but not visual spatial sketchpad tasks. So, for example, Salome and Badley in 1989 asked participants to maintain information in working memory while listening to either singing, music without singing, or no sounds at all, which is the quiet condition. Right? So the silent group performed best on the phonological loop task, but the group that listened to music without singing outperformed the group that listened to singing, right? So therefore, sounds of any nature, particularly meaningful sounds, interfere with our ability to maintain information in the phonological loop, right? Um, so that's one of the reasons why, for example, if you're in a busy coffee shop and you're trying to write a paper or something like that, why like other people talking on their cell phones or talking with their friends can be particularly distracting, right? Um, so the irrelevant speech effect also has implications for how to improve your memory performance, right? So it suggests that studying in a quiet room would lead to more efficient learning, um, because you can process information in the phonological loop more efficiently. And it also contradicts rather, something called the Mozart effect, right? So the Mozart effect is the purported finding, that's actually a widespread myth, that listening to Mozart can actually improve your memory efficiency, right? But there's actually no, like I said, no evidence for that, particularly when you're trying to learn information that's phonological or linguistic based in nature, right? So the best thing you can do, kind of in accordance with the irrelevant speech effect, is to make sure you're studying in a quiet environment. So I just wanted to show you one more experiment demonstrating the irrelevant speech effect. So this experiment by Colley and Welsh in 1976, they had participants listen to or view consonants rather while listening to either a relevant speech or a quiet condition. And recall was obviously better in the quiet condition, and this became known as the irrelevant speech effect. And the idea is that the irrelevant speech occupied the phonological loop and interfered with participants' coding of the consonants. And finally, there's a lot of evidence from neuropsychological case studies that seems to support the phonological loop as conceptualized by Badley and colleagues. So, for example, in the 1980s, Valor and Badley um, examined a patient with selective damage to the phonological loop as a function of damage to the left frontal cortex, right? So they examined a patient who with damage to the left frontal cortex, and the patient tested normally in most areas of cognitive functioning. However, her working memory was impaired as measured by digit span tasks. So, what is the evidence that her phonological loop wasn't functioning other than her limited digit spans? She also didn't show a typical word length effect, right? So there was no difference in her working memory performance whether the words were short to pronounce words or long to pronounce words. And her working memory performance was also unaffected by phonological similarity. So her performance for words and letters that rhymed or sounded similar was equal to her performance for words that didn't rhyme or sound similar. So what that suggested in particular, and what Badley and colleagues kind of reasoned from this patient, is that most likely she was compensating for her phonological loop deficit by using her visual spatial sketchpad. So we'll talk about the visual spatial sketchpad next. Okay, so now that we've talked about the phonological loop in detail, we are going to shift our focus to one of the other components, which is the visual spatial sketchpad. Okay, so as the name suggests, the Visual Spatial Sketchpad stores visual and spatial information for short amounts of time in the activated contents of consciousness. So it is largely independent of the phonological loop as long as attentional demands are low. And like the phonological loop, it is a short-term memory system designed to hold visual and spatial information for short periods of time of up to about 30 seconds. And recent research suggests that it's likely that visual and spatial information may be represented by different subsystems, but just for purposes of simplicity, we're going to talk about them as though they're utilizing the same system. So we're going to sort of put them together, right? So what do I mean by activated contents of consciousness? Well, the visual spatial sketchpad is open to conscious introspection. So, for example, we experience the visual spatial sketchpad when we retrieve what a familiar person looks like, right? Or if you have a mental image of your best friend's face kind of in your mind's eye, it is being represented in the visual spatial sketchpad. When you close your eyes and maybe think of the Manhattan skyline, okay, you're using your visual spatial sketchpad. If you glance briefly at a map while driving and then try to figure out where you are and how you're supposed to kind of get off the highway and get to your destination, that would utilize your visual spatial sketchpad to represent that information and also kind of manipulate the different locations. So like the phonological loop, the visual spatial sketchpad kind of occupies this role in cognition that brings thoughts and perceptions into your conscious awareness. So thus, whatever you're attending to visually in the moment is kind of the contents of your visual spatial sketchpad, right? So now I'm going to show you, just like I did for the phonological loop, I'm going to show you some classic experiments in memory science that seem to support this idea of the phonological loop as conceived by Alan Badley and colleagues. A classic experiment on the nature of the visual spatial sketchpad comes from Brooks' 1968. So, Brooks' original purpose was to explore the nature of imagery and how we create mental images, but his experiment actually provides an excellent example of the independence of the visual spatial sketchpad from the phonological loop. So basically, if you were a participant in Brooks's study, you were told to imagine letters that weren't actually present, such as the letter F, right? So because participants were asked to create a visual image, we can assume that the representation of this image is being held in the visual spatial sketchpad, right? And keep in mind that participants could not actually see the letter F. They only had a mental image that they themselves conjured up on which to base their decisions. So participants were then asked to make judgments about the letter, such as whether the angles in the letter were obtuse or greater than 180 degrees, or acute, which is less than 180 degrees. So basically, is the angle made up by the line that goes straight up and the line that goes straight out to the right, acute or obtuse, right, was their task. So participants had to rely on their image of the letter and were not allowed to physically draw one, right? So most tasks found this task really challenging, or most participants found this task really challenging. And so what Brooks manipulated concerned how participants made their responses. So responses were made by speaking the letters out loud, which would task the phonological loop, tapping them out with their hands. So one tap for yes, two taps for no, which would be a motor task, or pointing to a field with an array of Y's and N's for no, which is visual spatial, right? So there were three different conditions. One where they said yes or no, which tasks the phonological loop. One where they're tapping them out with their hands. So one tap for yes, two taps for no, and one where they're pointing to an image with an array of Y's for yes and N's for no. So note that neither the speaking condition or the tapping condition requires the visual spatial sketchpad, right? So only the pointing condition would task the visual spatial sketchpad, right? So because they're already utilizing the visual spatial sketchpad to conjure up the image of the F and also to actually answer the question regarding the angles of the letter, right? Then we would expect their performance to be reduced only in the pointing condition, which also tasks the phonological loop, right? And so when Brooks examined the results, he found that participants were more accurate and faster when they either had to speak the answer or tap the answer than when they had to point to the array. So, consistent with his hypothesis, only the visual response task interfered with the imagery task. And because of the interference in the visual domain, performance decreased on the imagery task, right? So thus, as we've seen with the phonological loop, if you have two concurrent tasks that both tax the visual spatial sketchpad, then your performance is going to be reduced. So, in addition to the Brooks 1968 letter F experiment, most other experimental investigations of the visual spatial sketchpad either focus on what's called the mental scanning paradigm or the mental rotation paradigm. So, we'll go ahead and start with the mental scanning paradigm. So this was pioneered by a researcher by the name of Coslin in the late 1970s, early 1980s. And so basically, if you were a participant in a mental scanning experiment like the one shown, basically you would be shown a map of an imaginary island. And that map would depict various objects and locations objects and locations within the map, right? So, for example, you might see a little grass hut, you might see a tree, you might see a hill, and various other landmarks. And so, your job as a participant would be to study that map until you could reproduce it from memory, right? So, you would study the map and all of its locations and landmarks long enough for you to be able to generate a mental image of the map using your visual spatial sketchpad. And then the map was taken away and participants were asked to mentally picture the map, okay, and mentally scan the picture from one location on the map to another, okay? And so for example, they might say, imagine yourself at the tree north of the hill and traveling from that tree to the hut on the other side of a river or something like that. So you would conjure up an image of the map in your mind, conjure up an image of the tree in the map, and then you would sort of mentally walk along the map to the hut location. And so when you were done mentally scanning the map and walking to your location, you would press a button. And essentially, what Coslin and colleagues found is that scanning times were linearly related to the physical distance between the locations on the map, right? So, what it seemed was happening was subjects were conjuring up a mental image of the map and then literally in real time kind of traveling between the locations, right? So the more uh, further apart the two locations were, the longer it would take participants to mentally scan them, right? And this really illustrates the essence of working memory, right? Because the work of working memory is taking an object in your environment, creating a mental image of that object, internalizing it, okay, and then manipulating it in some way. So, quite literally, what participants were doing is conjuring up the map, scanning the locations, and imagining themselves traveling between those locations, right? So, again, scanning times were directly related to the physical distance between locations on the map. So the further apart the locations were, the longer it would take you to mentally scan the distance between the locations, and the closer they were together, the less time it would take you to mentally scan between the two locations. So, in addition to the mental scanning paradigm that I just talked about with Coughlin and colleagues' work, we also have something called the mental rotation paradigm. And this was really started with Shepard and Metzler around the same time. And so, what Shepard and Metzler did in their famous experiment is they gave participants a task like this. So if you were a participant in their experiment, you would see a pair of images, right? So you can see in the panels A, B, and C, right? Those are three different pairs of three-dimensional objects. And so for some of the pairs, the first image, or the second image rather, was the identical object depicted in the first image, only it was rotated to a different angle, right? Whereas in other pairs of images, the second image was a totally different object, right? So you would either see a pair of the same two objects, just the second picture in the pair would be the same object rotated to a different angular view, or you would see a pair of two different objects. And so your objective as a participant in Shepard and Metzler's study was to indicate, yes, these are the images of the same object, or no, there are two different objects shown in the pair. And so, just like Coughlin and colleagues in their mental scanning experiment found that the reaction time for mental scanning was linearly related to the actual distance of the two locations on the map, what Shepard and Metzler found is that the degree to which the second image was rotated was linearly related to the reaction time, or the number of seconds it took participants to say, yes, this is the same object, right? So when the two images depicted the same object, just the second picture was the object rotated in space, the more rotated the object was in the second image, the longer it would take participants to give a correct yes response. And so what that illustrates is what participants are doing is rotating the object in real time, just like people in the Kostler experiment were mentally walking along the map in the mental scanning paradigm, right? So you would conjure up an image of the second picture and then attempt to rotate it. Or, excuse me, you would conjure up an image of the first picture and then attempt to rotate it so that it matched the second picture. And obviously, if you're actually rotating it in real time, the more rotated it is, or the higher the number of degrees of angular rotation, right, the longer it's going to take you to say, yes, these objects are the same, right? And that's the essence of what is happening with the visual spatial sketchpad in your working memory is you see an object in the environment, and that is converted from your sensory memory, your iconic memory, into your visual spatial sketchpad. The visual spatial sketchpad creates a mental representation of the object. Okay? You conjure up that object in your visual spatial sketchpad, and then you manipulate it, either by scanning or by rotating in real time. And this is a nice replication of exactly what we see in the Shepard and Metzler study. So this study shown is also a mental rotation experiment, but instead of rotating the objects to see if they match, basically what the participants were doing is they were shown images, okay? And basically what they had to do is they had to fold a cube until the arrows matched, okay? So they had to fold segments of a cube until the arrows matched and then see what the object looked like. But they didn't have, physical paper cubes or plastic cubes that they could manipulate. Instead, they had to mentally fold the object. Okay. And so again, what they found is the amount of time it took them to choose the correctly matching object was directly related to the number of folds, mental folds, they had to make in order for the arrows to meet, right? So just like we can mentally rotate objects in space, we can also mentally fold objects in space, right? Because our visual spatial sketchpad has created a mental representation of a three-dimensional object, and we can use our sketchpad to sort of move it and fold it and manipulate it, even though it's an internal representation rather than being a physical object. So what other insights can I share regarding the visual spatial sketchpad? Well, there's actually a lot of interesting boundary conditions and sort of interesting patterns of results. One of which is differences in biological sex. Right? So tasks such as mental rotation tasks or mental scanning tasks are often used to assess people's aptitude for different types of jobs, right? So for example, if you want to be an architect or an engineer or something that is likely to require extensive spatial reasoning, these tasks might indicate whether you would be good at that job or not. And a lot of research has suggested that biological males tend to excel more at these spatial tasks than biological females. So one study by Tsai and colleagues in the late 90s found that female engineering students from the University of California, Berkeley, were less good at performing these sort of spatial manipulation tasks, and were also less likely to do well on a very difficult graphics course. And in fact, this pattern of results was so consistent that up to 25% of female engineering students would routinely earn about a 60% in the course. Fortunately, though, Tsai and colleagues were able to get a sense of how these male engineers, what strategies they were using on these spatial manipulation tasks. And on the basis of this kind of self-report, they were able to come up with a series of very concrete strategies and teach these strategies to the female engineering students such that they were able to implement them. So the good news about that is even though there are these intrinsic differences in terms of spatial awareness and manipulation ability, these strategies can be verbalized and implemented. So you can provide sufficient curricular support to overcome these disparities. And kind of along the same lines, looking at inherent spatial manipulation abilities. Atuka and colleagues investigated how visual tasks interfered with math performance. So they found, for example, that people that routinely do well on arithmetic assessments are more likely to use both visual and auditory strategies to help them with mental arithmetic, whereas those that struggle in math related tasks are more likely to just use auditory strategies. So what they found is that the higher performers in math whose performance was more interfered with, um, so the people that genuinely that do well in math and utilize both visual and auditory information were actually more hampered um, by introducing a secondary visual spatial task, right? So because they were already using their visual spatial sketchpad to do the math problems, when they had to do a concurrent visual spatial task, their performance on the math problems actually suffered compared to less proficient um, participants who were less proficient in math, who were solely using auditory information via the phonological loop. So because the math information was localized to the phonological loop instead of also being processed by the visual spatial sketchpad, the secondary task didn't interfere as much. Another interesting study looked at math experts in Japan who routinely used a mental or routinely used an abacus. And they were so experienced with using the abacus that they were actually able to do mental calculations by imagining that they had access to an abacus. So mentally creating an image of an abacus and using that mental image to do these arithmetic calculations. So they could, for example, mentally add and subtract up to 15 numbers, each comprising from 5 to 9 digits. They also had extremely high digit spans. So digit spans are typically about 7 numbers for most people, whereas their digit spans were twice that, about 16 digits, whether they were doing forwards or backwards counting. Um, but one interesting thing is that their enhanced memory span was exclusive to digits. So their span for other verbal materials, such as consonants, for which the mental abacus wouldn't provide a lot of benefit, was no better than the control group. And as would be expected, if the experts were relying on visual spatial imagery, their digit span was markedly disrupted by a concurrent spatial task, right? So if you showed them a map and asked them to traverse to different locations, or if you had them draw an object by conjuring up a mental image, that would severely inhibit or disrupt their ability to do the mental counting, whereas the performance was less disrupted by disruptions in the phonological loop, such as articulatory suppression, again because they were utilizing the visual spatial sketchpad and not the phonological loop. Another really interesting experiment suggests that the visual spatial sketchpad doesn't operate in unison or it doesn't operate alone, but rather it works by interacting with other structures in working memory, such as the phonological loop. So, for example, Pearson and colleagues in 1999 presented participants with 4, 6, or 8 shapes, right? And they were very simple shapes like a circle, a square, or a triangle. And he asked them to use the shapes to create and draw a novel object that they were then to describe to the experimenter. So because this was a novel object, the act of coming up with a novel object using the three shapes was believed to task the visual spatial sketchpad, whereas the act of generating a name for the novel object was thought to rely on the phonological loop. So the task again required both the visual spatial sketchpad for imagining the novel object and the phonological loop in order to come up with a novel name for the object. So in some blocks of trials, which are just mini experiments, participants performed a concurrent or second task, which was either tapping their finger into a figure 8 pattern, which would rely on the visual spatial sketchpad, or repeating the word go every 500 milliseconds, which would task the phonological loop. And not surprisingly, what they found is that the tapping pattern in the figure 8 interfered with the visual spatial sketchpad. So that made it harder for the participants to come up with a novel object that utilized all of the shapes. Whereas the saying the word go over and over again, because that tasked the phonological loop, it made it harder for people to come up with a novel name for the object, which is also a phonological loop task. So now that we've talked about experimental evidence for both the phonological loop and the visual spatial sketchpad, now we're going to focus our attention on a third component known as the central executive. So the central executive is a core component of Badley and Hitch's multi-component model of working memory. So it's responsible for overseeing and coordinating information between the visual spatial sketchpad and the phonological loop. So it oversees and coordinates the various subsystems of working memory, and it also manages various cognitive processes. So the central executive isn't responsible for storing information. Instead, it regulates the flow of information and operations within working memory. So now we're going to go over some of the functions and characteristics of the central executive. So one of the most important components of the central executive, or tasks of the central executive, is to function as an attentional controller. So the central executive is responsible for three different types of attention. So the first is selective attention. So selective attention would be directing attention to relevant information while ignoring distractions. So for example, if you were studying in a busy coffee shop in Macon, like Z-Beans, for example, your selective attention would be engaged if you were focusing on writing your paper, and so your central executive would be engaged to direct your attention to reading the sentence that you just wrote and maybe processing something that you read in an article that you want to use for your paper, and filtering out all of the background noise. So the sound of the coffee machines, the sounds of other people having conversations, and so on. Sustained attention would be engaged by the central executive whenever you maintain focus on a particular task over a period of time, right? So if you stay focused on writing your paper for an extensive period of, say 4 or 5 hours, that would be one of the functions of the central executive. And lastly, we have divided attention. So divided attention is typically engaged whenever you are trying to do multiple concurrent tasks simultaneously, right? So allocating attention across multiple tasks or sources of information. right? So, for example, if you're driving and you're focusing on, where your car is on the road, where your destination is, but you're also listening to a podcast or listening to the radio, that would be an example of divided attention. So, one interesting study designed to probe the role of the central executive in working memory comes from the work of Teasdale and colleagues in 1995. So, what they did is they asked participants to generate random numbers at a rate of about one number per second. But this actually isn't as easy as it seems, right? Because you must regulate the generation of numbers to ensure that you're not making any sort of obvious pattern. You also must do it in rhythm, right? So if you try to do it yourself, you'll find that it actually requires quite a bit of attention and focus to make sure that a clear pattern isn't developing and that you're keeping that rhythm of one number per second. So um, when Teasdale did this experiment, they probed participants about every 2 minutes and asked them what they were thinking about. When participants reported daydreaming and not thinking about their current task, not surprising, right, given how repetitive the task is, their patterns tended to be non random, such as sequences like 1, 2, 4, and 8, where the numbers were doubling. But when they reported that they were not daydreaming and instead they were concentrating on their task, their numbers were better approximations of randomness. Thus, when people's attention was diverted, as it was when they were daydreaming, insufficient attentional resources remained in order for them to devote their attention to the number generation task, right? So the implication is that the central executive, when directing attention to the number generation task, allowed participants to better produce random digits in their working memory. Another important component of working memory is what we call updating, monitoring, and inhibition. So basically, continuously updating and monitoring working memory contents to keep it relevant to the current task, and also suppressing automatic or prepotent responses that are not relevant to the current goal. Okay, so I know that seems very abstract. So, in just a couple of slides, I'm going to talk about how psychological scientists actually measure these updating and monitoring and inhibition processes. Another critical component of the central executive is planning and decision making. So, whenever we formulate strategies, make decisions, or engage in problem solving, these processes would engage the central executive. So, as I mentioned before, now we're going to focus on how memory scientists actually measure the central executive. So, cognitive psychologists have a variety of methods for assessing the central executive component of working memory. And working memory is responsible for high level or high order cognitive processes like attention, control, problem solving, coordination of the other memory systems, etc. So now we're going to go through some of the common tests or tasks that psychologists use to measure the central executive. Okay, so first we have dual task paradigms. So in dual task paradigms, participants are required to perform two tasks simultaneously, right? And the rationale is that if both tasks depend upon the central executive, performance on one or both tasks will decline due to the fact that both tasks require the same cognitive resources. So an example might be a participant might be asked to repeat a series of numbers while simultaneously solving a series of math problems, right? And we would expect performance to decrease on one or both tasks as they both require the central executive. So next we have complex span tasks. So these tasks involve maintaining information while simultaneously processing other information. So they are designed to tax the central executive by requiring simultaneous storage and manipulation of information. So one example is the operations span task, which requires participants to solve a series of math problems, which is considered a form of manipulation, while also remembering a sequence of unrelated words, which requires storage. So the number of words recalled correctly indicates the efficiency of the central executive at maintaining attentional control for both of those tasks. Another method for studying the effect of the central executive on working memory is to use what is known as the in-back task. So in the in-back tasks, participants are presented with a series of items, usually letters or numbers, and are cued to report the item that was presented in items earlier, where n varies depending on the experiment. So for example, in a typical two-back paradigm, participants would be told that they would be presented with a string of digits, and after the presentation of each digit, they would be cued to report the number that was presented 2 items earlier in the sequence. Thus, if the participant was shown 429, the participant would need to enter either 4 after the digit 9 was presented. In other variations of the task, the cue is presented after digits at random. So to complete the in-back task correctly, the central executive must continually update the contents of working memory such that if needed, the in-item back is available for report. Research using the in-back task supports the notion that the central executive controls the content of working memory and helps participants to continually update its contents so that they are relevant in accordance with the task. Another type of task that measures the central executive is what's known as a task switching paradigm. So these tasks measure the ability of the central executive to switch attention between 2 different tasks or activities. So for example, participants may alternate between tasks according to a given rule, which essentially requires the flexible allocation of cognitive resources. So for example, a participant might switch between a number classification task and a letter classification task based on a cue. So the reaction time and errors made when switching tasks compared to repeating the same task would indicate the efficiency of the central executive. So another task that I'm sure at least some of you are familiar with is the Stroop task. So the Stroop task assesses the central executive's ability to inhibit automatic responses. So participants are asked to name the color of the ink in which a word is printed rather than reading the word itself. And this requires overriding the automatic process of reading. Right? So for example, if the word red is printed in blue ink, the participant must say blue instead of red. The difference in response time between congruent, where the word and the color match, and incongruent, where the word and the color do not match, trials indicates the central executive functioning, right? So the only group of participants that we would expect not to show a Stroop effect would be, for example, preschool children who don't know how to read, right, and only know their colors. So they would find this task very, very easy because there's no dominant reading response that their central executive has to inhibit, right? So if all the child knows is their colors, they would find it very easy to see the word red and say blue, because obviously they can't read the word red. Uh, and so this finding that, for example, preschool children don't show a Stroop effect is known as the differential practice effect, right? Um, People have also used the Stroop task to measure the central executive in clinical populations. So, for example, if you present combat veterans with a Stroop task where some of the words are related to war and military and combat, they'll show a stronger Stroop effect or a longer reaction time for those words. Just like if you show someone who is depressed, for example, words like sad and hurt and hopeless, they'll show longer reaction times when given this color naming task. And also, when you show people taboo words like profanity or sexually explicit words, the central executive has a harder time inhibiting that reading response, right? Because the words themselves are attention getting. They're very salient, and so the central executive has to work harder to suppress that dominant response of reading the word. So, another example of a central executive task that I referenced earlier that I wanted to revisit was the random number generation task, right? So, in these tasks, participants are asked to generate a sequence of responses, either numbers or letters, in a random manner, in a random of as a manner as they can, right? So the central executive's role in this case is the ability to inhibit predictable patterns of numbers or letters and produce truly random sequences. So, for example, a participant might be asked to generate a random sequence of numbers between 1 and 10 at a steady pace, and deviations from randomness can be analyzed to indicate less central executive control or impairment of the central executive. So, really So, one of the last things I wanted to discuss before we continue with other components of the working memory model is some interesting research looking at how language immersion programs affect the central executive. So, for example, French immersion programs are extremely popular in Canada because Canada has two official languages, both French and English. And also because many parents are told that if their children complete French immersion, it actually leads to enhanced cognitive functioning and specifically better working memory. So researchers at York University in Toronto decided to assess these claims that French immersion improves cognitive functioning, most notably working memory. And so they compared three different groups of university students. They compared monolinguals, or students that spoke only English. They compared former French immersion students who at one time could speak both French and English, but now could no longer speak French. So those were the lapsed bilinguals. And lastly, their third group of students were French immersion students who continued to be able to speak both English and French. And so what they did in this procedure is they had participants complete two tasks. The first was what's called a flanker task, which is a measure of working memory, and participants had to indicate as quickly and accurately as possible which direction a red arrow was pointing, either left or right. And then in the baseline condition, the arrows were presented alone. And in the neutral blocks, the little arrow was flanked by black squares. And in mixed blocks, the little arrow was surrounded by black arrows that were either congruent or not congruent. So the second one was also a working memory task. And in this task, participants had to indicate whether the stick figure on the current trial matched one from the initial display and was the same stick figure that appeared on previous trials. So basically, after the participants completed the two tasks, the researchers found that the groups did not differ in their ability to perform the flanker task, but they did differ in their performance on the working memory task. Specifically, bilinguals were significantly more accurate in the working memory task than the lapsed bilinguals or monolinguals. So these results suggest that French immersion may benefit working memory, but only if the individuals continue to speak two languages. Thus, being a functioning bilingual seems to indeed benefit your working memory, which makes sense if we conceptualize working memory as predominantly being about attentional control, right? So being able to think of a word and either attend to the English definition or the French definition, okay? And also to sort of go in and out of both English and French when you're conversing with other people. Okay, so that concludes our discussion of the central executive. And now I'm going to focus on the last component of the working memory multi-component model, which is the episodic buffer. So the episodic buffer is the most recent component to be added to the multi-component working memory model proposed by Badley and colleagues. And so essentially what the episodic buffer component tries to explain is how information is integrated between, for example, the phonological loop and the visual spatial sketchpad, and also how working memory interfaces effectively with long-term memory. So I'm going to give you a bunch of definitions and then I'll go into more detailed explanation. So the episodic buffer is a short-term memory system that holds information integrated across auditory working memory, visual spatial working memory, and long-term memory for a brief period of time. And because it maintains information already integrated across modalities, it serves as a point of interface between working memory and long-term memory systems. So the episodic buffer provides needed meaning or semantic-based information to the working memory system as a result of interfacing with long-term memory. So, for example, when you retrieve information from long-term memory, such as the directions to your cousin's apartment, this information is briefly maintained in the episodic buffer before it's converted into directions into the phonological loop or a visual map in the visual spatial sketchpad. Okay, so the episodic buffer is essentially the conduit or the connection between what's already stored in your long-term memory system and what's currently stored in your working memory system across the different components. The episodic buffer also allows new information to be integrated before it reaches your long-term memory during encoding. So, for example, if you watch a ballet performance, it will involve dance information being processed in the visual spatial sketchpad and music information being processed in the phonological loop. And the episodic buffer will integrate the dance and the music with information in your long-term memory related to meaning before the experience is stored in long-term memory, right? So the new information comes in the form of dance movement in your visual spatial sketchpad, the sound of the accompaniment being played in your phonological loop, and then existing schemas or concepts related to dance and rhythm will be integrated with that new incoming information before it's stored in your long-term memory. A lot of the information that we currently have available about the function of the episodic buffer comes from patients with amnesia who have very impaired encoding into long-term memory, but normal working memory. Right? So when encoding stories, they seem to be able to maintain more than 7 items of information in mind while reading the stories, but the patient forget the stories later, even though their immediate or short-term memory extends past the usual duration of working memory, right? So they're able to read incoming information from the story and hold it in their working memory, but it never actually passes from working memory into long-term memory because of issues with the episodic buffer. So Badley and Wilson in 2002 argued that this is because of the integrated nature of the episodic buffer. The episodic buffer allows for understanding even though the patient forgot the information, right? So even though the patient had difficulty taking what they read from the stories from their working memory to their long-term memory system, some of the information currently residing in long-term memory of those patients was still integrated with information in their long-term memory, right? So even though they wouldn't remember the story later, while they were reading it and still processing it in their working memory, the episodic buffer allowed them to kind of fill in some components of the story. Maybe they were able to understand or comprehend the words, or maybe they had a general sense of how stories generally work, with a protagonist and an antagonist, because the episodic buffer was able to integrate all of that new incoming information in working memory with whatever residual information the amnesic patients had in their long-term memory. Okay, so the very last thing we're going to talk about is working memory and the brain, right? So what evidence from neuroscience do we have with respect to working memory? Well, Warrington and Chalice in 1969 wrote up a case study about a young man with the initials KF. So his brain was injured as a result of a motorcycle accident in England, and his long-term memory was unaffected, both in terms of his ability to learn and retrieve or learn new information and also to retrieve old information. So his long-term memory was perfectly intact, but in contrast, his working memory was severely damaged. So his working memory was severely impaired, such that on a digit span task, he could not recall more than 2 digits at a time when he was tested auditorially, right? So his phonological loop was clearly impaired. But his visual working memory was somewhat better, though still impaired. So this pattern suggests that the problem was more with the phonological loop than the visual spatial sketchpad. Subsequent examination of KF's brain confirmed this pattern. So he had damage in the left temporal lobe in areas typically associated with speech comprehension. So from that, researchers could deduce that the phonological loop was localized to the left temporal lobe. So another example of a critical study was one conducted by Joe Nides in 1995, and it was one of the earliest PET studies to look at memory phenomena, testing Badley's working memory model. So Janides examined the brains of participants engaged in tasks to measure the phonological loop or the visual spatial sketchpad. In the task designed to examine the phonological loop, participants watched a sequence of letters at a rate of 1 letter every 3 seconds. If a given letter was the same as one 2 spaces back, the participant indicated this by saying yes. If not, the participant said no. So this is basically the in-back task. And most people will do this task by mentally rehearsing the digits as they appear. Thus, even though the presentation is visual, it is sensible to consider this task as requiring the phonological loop. To occupy the visual spatial sketchpad, participants saw 3 dots presented in different locations for a 200 millisecond interval. The dots then disappeared, and 3 seconds later, a circle appeared. The participants indicated whether this circle marked a spot where one of the dots had been before. So what the PET data showed was that the 2 tasks led to different patterns of activation in the cerebral cortex. The phonological loop task was associated with activity in Broca's area in the left frontal lobe, as well as areas in the left parietal lobe. In contrast, the visual spatial sketchpad task led to activation in the right occipital lobe, which makes sense, as that's a central visual processing center of the brain, as well as the right parietal and right prefrontal lobes. Thus, the distinction between the visual spatial sketchpad and the phonological loop is supported by PET studies, which show different activation patterns for each task. Indeed, these data suggest that the basis of the phonological loop may be in the left hemisphere, but the basis for the visual spatial sketchpad may be in the right hemisphere. So the early neuroimaging data suggests strong differences between the neural basis of these two systems. Other neuroimaging techniques have also been used to examine the neural substrates of working memory. So neuroimaging data from fMRI studies confirm that the central executive is an important component of working memory. Areas of the prefrontal cortex that are known to be involved in other attentional or monitoring tasks appear also to be active during working memory tasks, including digit span and other verbal working memory tasks. So, for example, PET studies and fMRI studies agree that verbal working memory tasks activate the right dorsolateral prefrontal cortex as well as the anterior cingulate. The anterior cingulate is located toward the back of the prefrontal regions of the brain. Both of these brain regions, the right dorsolateral prefrontal cortex and the anterior cingulate, are important in self-regulation, attention, and cognitive monitoring, as well as verbal working memory. In an interesting study of the neural correlates of the central executive, Chin and colleagues 2014 required participants to scan visual arrays or auditory lists for oddball items. That is, items that did not fit into a pattern being represented. The oddball items for visual tasks could be a green dot presented among red dots. The oddball item for an auditory task could be a note of higher pitch presented among other notes of the same lower pitch. These two tasks are both within system, so they require less supervision from the central executive. In a multisensory task, the participant had to detect whether both the color and pitch were oddballs. This task requires more intervention from the central executive. So in this study, the anterior cingulate showed a crucial role in detecting the oddball item, and even more so when the task became difficult, as is the case in the multisensory condition. Thus, this study confirms the importance of prefrontal regions such as the anterior cingulate controlled by the central executive, right? So if they had to just focus on oddball items in the visual spatial sketchpad, so if they had to just focus on finding that green dot among red dots, that doesn't require a lot of secondary supervision from the central executive. And similarly, if they just had to focus on oddballs in the phonological loop, right, spotting or hearing a higher note among lower notes wouldn't require a lot of additional processing from the central executive. But if they had to look for the oddballs across the two different domains or types of tasks, right, that would require the central executive to both pay attention to both components of working memory and also to kind of divide attention between them, right? So when the central executive was engaged, and they had to focus on both information in the visual spatial sketchpad and information in the phonological loop. They found patterns of activation in the prefrontal lobes and the anterior cingulate cortex, which suggest that those are kind of the neural substrates of the central executive. Okay, thank you guys so much for your sustained attention throughout this entire lecture. And please let me know if you have any questions, and have a wonderful day.